This is day one of chapter 3. Basically, chapter 3 is logs and exponents. And for our first day here, we're going to look at a particular type of equation, an exponential equation. What makes exponential equations is the fact that the variable we're solving for is in the exponent. Now, all of these could be solved using logarithms, which we're going to get to in a couple days. All of these could be solved using graphing technology, which we'll talk about a little bit later in the chapter. But we're going to focus on one particular type of strategy for these types of problems. And that strategy is going to involve getting both sides of the equals to be powers of the same base. Let me zoom in a little bit here. This. Make sure this is focused, or as best as it can be. Okay, so for number one, this equation already has both sides to be base 7. Okay, our intermediate goal for most of the problems in the rest of this worksheet is to be able to get it to look like this. Once it looks like this, what you're allowed to do is just set the exponents equal to each other. Now, sometimes the equation you get left when you do this is a simple little mental math. Maybe it involves some factoring. I think we get to those tomorrow or the day after. Whatever it takes to get it solved. In this case here, bring over the 2x, divide by the 4, and we get a solution of x is equal to -5. One of the things we've talked about with almost every type of equation solving we've done in the book is the fact of when should you be checking answers. As far as the risk of extraneous solutions, extremely low risk with these equations. So it's not necessary to check for the purposes of extraneous. Checking for the purposes of finding an arithmetic or algebra mistake is always advisable if time permits. Okay, number 2, level up from number 1. Both sides are not powers of the same base. Okay, your two sides are not powers of the same base. By the method that we're using today, we want to get them to be powers of the same base. So, for example, we can rewrite 9 as base 3. I'm not going to do anything to the left. And then apply basic rules of exponents here, a base to a power again. Means we multiply those exponents. And now we hit that intermediate goal of both sides are powers of the same base. So keep things positive. Let's bring this over here. Bring that over there. So x is equal to 1/2. Again, low risk of extraneous solutions. You do not have to check for that purpose. If time permits, though, always a good idea to check for arithmetic or algebra mistakes. All right, let's say I might have to zoom back out a little bit to have this fit. All right, level up from that one, number 3. Very clearly, the base 9, base 27 is different. Easiest way to go with this is those guys are both powers of 3. So we're going to rewrite 9 as 3 squared. Rewrite 27 as 3 cubed. Using our rules of exponents, that's 3 to the 4x minus 2. That's 3 to the 3x plus 12. And now we hit that intermediate goal of both sides powers of the same base. Our exponents are cleaned up. Oops, that's right. And then we solve what's left. All right, so for this one here, bring that 3x over, bring the minus 2 over, and we're done. All right, number 4, very often with these problems, radicals get mixed in addition to the exponential notation. So this is an example that addresses that. Recall that the square root of 5 is the same thing as the 5 to the 1/2 power. Raising to the 1/2 power and taking the square root are algebraically equivalent. So once we make that one move, very similar set of steps that we saw with the first three examples. This will be 5, 1/2 x plus 2, 5, 2x plus 3. We got the intermediate goal of both bases being the same. Set the exponents equal to each other and solve what's left. My personal preference for this one is I would multiply through by 2 to clear out that fraction. Now we're assuming we're doing this without technology, so to keep things simple, that's a good choice. Let's get that over there, that over there, and we get x is negative 2/3. All right. Mixing in some fractions, which very often means negative exponents when you're in this little corner of the math world. Let me copy these two down so I can slide the paper up where you guys can see this. All right, so these are the next two problems, 5 and 6. We want to get 1/16 and 8 expressed as powers of the same base. Okay, one way to do that is 16 is 2 to the negative 4 power. 2 to the 4th gives you 16. The negative exponent moves top bottom. This is 2 to the 3rd, the 2x minus 1. 2 to the negative 4x minus 4 equals 2 to the 6x minus 3. And there's that intermediate goal that we shoot for. Set the exponents equal to each other and solve what's left. So we'll keep it positive, bring that over there, and out there. And we get a final answer of x is equal to negative 1. All right, number 6, there are a few different ways you can solve this. The way that I'm going to show you is not necessarily the most efficient way, but it reviews some other rules of exponents that I want to include in here. What I'm going to do is express 9 and 27, both as powers of 3. So this will be 3 squared to the 2x plus 1, 3 cubed to 5x. So that's 3, I'm going to potentially run out of room here, to the 4x plus 2 over 3 to the 15x. And then one thing we can do, again, not necessarily the most efficient way, but I wanted to include this exponent rule. When you're dividing bases that are the same, you subtract exponents. So that's going to be 3 to the 4x plus 2 minus 15x. And then the last thing I'm going to do, I'll do two things at once here. Anything to the 0 power is 1. So this is understood on the right-hand side to be 3 to the 0. So I can clean up and combine my like terms here. So that's a negative 11x plus 2 equal to 0. Negative 11x is equal to negative 2. X is 2 11ths. Okay. So that brings us up to number 7 for today's class examples. 64 and 16, we have choices here. We could go base 4 or base 2. Either one would work. They would both lead us to the same set of answers. I don't think we've done base 4 yet today, so we'll do that as something different. It's 4 to the third to the 2x, 4 squared to the 3x. So that's 4 to the 6x equals 4 to the 6x. 6x equals 6x. So what happens here is the left-hand side always equals the right-hand side. This is all real numbers. Any real number you choose, plug it in there. Left side is always going to equal the right side. Or in other words, we have an identity, all describing the same situation. Okay, so that's one of the kind of special cases, so to speak, that can happen. We don't end up getting one specific value. Any value would work. Okay, for number 8, we can go base 6. We get negative 3n equal to 0, n is equal to 0. All right, for some reason, some students get a little weird when 0 is a solution, thinking 0 is not allowed to be a solution. You can have 0 as a solution. This is the case right here. If you plug that into the original equation, 3 times 0 is 0, 2 minus 0 is 0, 6 to the second is equal to 36. So not that this is a special case, but it is possible to have 0 as a solution. It's a valid number. All right, number 9. So we have 5 to the x times 25 to the x equals 5 to the 3x minus 1. All right, so that 25 we're going to want to get in terms of base 5, so it matches everything else. So that becomes 5 to the 2x, 5 squared raised to the x power. And one of the things that makes this problem a little different than what we've done so far, we have to use the addition rule for exponents. So it's 5 to the 3x, multiplying two bases that are the same. The base stays the same, add the exponents. So we get 3x equals 3x minus 1. 0 equals negative 1. Now we're going to think about this the same way you thought about most problems when it comes to an equation solving situation where the variables drop out. If the variables drop out, you're left with a numerical statement that's either true or it's false. In this case, 0 equals negative 1. If that's a false statement, that means, or the way we interpret that, is there is no solution. No matter what x you pick, the left-hand side is never going to equal the right-hand side. You can write out no solution. You can use the 0 with the slash through it, whichever you prefer. All right, the strategy of getting both sides of the equation to be the same base also applies in a couple other variations in problem solving. These guys aren't as common as they used to be on the SAT, but they still pop up occasionally. They're in every once in a while you see them, depending on what version of the test you get. We're going to use that idea of dealing with bases being the same, setting exponents equal to each other, except it's not going to be quite as straightforward as 1 through 9. So for example, number 10, it says if 9 times 1/3 to the n power is equal to 3 to the n, what's the value of m plus n? Okay, so let me copy that here and then make room. So for number 10, we have 9 times 1/3 to the n equals 3 to the n. All right, so 9 is 3 squared. 1/3 is 3 to the negative 1. Again, it's 3 to the n. So that's 3 squared times 3 to the negative n equals 3 to the m. So that's 3 to the 2 minus n equals 3 to the m. Because when you're multiplying bases, you add the exponents. Right, now, we hit that intermediate goal of both sides being powers of the same base. We can set the exponents equal to each other. All right, now, instead of getting a single like x equals answer, what they're asking us for is what's the value of m plus n? So, how do we get m plus n from this guy right here? Well, if we bring the n over here, that gives us that value. Right, now, the thing that makes this different, or this type of question in general different from what we've done, is when we solve this problem, we never individually know what m and n are. We don't know what m equals, we don't know what n equals, and we don't care what they equal to answer this question. But we do know if we take them and add them together, you end up getting a 2. And for more challenging type of SAT or SAT-like tests, or questions within the tests, this tends to be the flavor, where you're not actually solving for an individual variable, just for a relationship between them. Now, again, as far as the big picture goes, this type of question used to be very, very common on the SAT. Not as common as it used to be. If it does pop up, it could be as straightforward as something like number 8, where it's simply straightforward, plug and chug, know your algebra skills, and get the job done. Sometimes it could be a little bit more challenging, like number 10. All right, so on to 11. We've got a similar idea here in terms of the SAT flavor. So I'm going to copy down what we know. So it's telling us x to the a squared over x to the b squared is equal to x to the 16th. X is greater than 1. A plus b is equal to 2. And they want us to know what a minus b is. They want us to, an equal sign, figure that out. All right, that x being bigger than 1, that's going to be a restriction that is not super critical today, but with what we're going to get to in a couple of days, a lot of the properties of what we do in this chapter rely upon that base. In general, can't be 0. In general, can't be negative. Can't be 1. It could be a positive fraction, or it could be anything bigger than 1. That's just incorporating stuff that don't necessarily have to know to answer this question today, but as we move through the chapter, that's going to be a big deal. All right, now to the here and now. We're dividing two bases that are the same, so that means we want to subtract those exponents. So that's x to the a squared minus b squared equals x to the 16th. So once we get these bases the same, we can set these exponents equal to each other. So a squared minus b squared equals 16. Now, a squared minus b squared, that's a difference of 2 squares. That can be factored. A plus b, a minus b equals 16. And now we're at the stage where we can use this factor right here. A plus b is 2. So this overall structure is 2 times something equals 16. Well, that's the something we're looking for. They want to know what's the total value of a minus b. Well, a minus b must be 8. Now, similar to number 10 that we just did, we don't know what a is. We don't know what b is. We don't know what x is. We individually never solve for any one particular variable. But we can, given that information, have enough facts and skills to be able to determine what a minus b must equal. All right, let's do a clean page for this. All right, last one for today's examples, number 12. Excuse me. Okay, if 3x minus y is equal to 12, then what's 8 to the x over 2 to the y? 8 to the x over 2 to the y. That's what I'm going to concentrate on first. Well, we've been talking about getting bases to be the same for now 12 straight problems. So what if we start off that way? That's 2 to the third to the x over 2 to the y. So that's 2 to the 3x over 2 to the y. So it's 2 to the 3x minus y. When you're dividing bases that are the same, the rule is that base stays the same, subtract the exponents. Okay, now that we're here, we see where that 3x minus y comes in, why that's important. 3x minus y is equal to 12. Now typically, I think that this question was a multiple choice. Wherever I saw this, it was probably an older SAT practice test, or maybe an actual question. They normally don't multiply things out like 2 to the 12th power on the SAT. It would probably be multiple choice where all the options were something in exponential form. As a non-calculator question, it would be highly unlikely they would expect you to multiply 2 to the 12th out. That would be something that would be acceptable to just leave like that. If it was a calculator active question, you certainly could type that in and figure out what 2 to the 12th is in non-exponential form. That was the last one, correct? Yes. All right, so that wraps up what you need to know for today. This lesson is done.